Hello everyone. Today we're going to be looking at trigonometric identities. So this is going to be kind of a beginning of a new chapter for us. We are moving on past triangles and angles, and we're going to be looking at trig in a different way. So let's go ahead and get started and see what we can do. Okay, trigonometric identities. I want to start by saying, how have we looked at trigonometry so far? So far, we've seen two big perspectives on trigonometry. We've seen what I would call unit circle trig, uh, and that included things like sine t, cosine t, etc. And you know that when we did unit circle trig, we often talked about going some distance around the unit circle, usually counterclockwise, some t value. And we would go some t value around the unit circle, and we'd figure out what terminal point it took us to, and that would tell us the x and y value, and that would be cosine and sine. Um, and then we also looked at what I would call triangle trig. And in our lessons about triangle trigonometry, it was usually labeled sine of theta, cosine of theta, right? There was some angle of interest that we were focused on, and it was usually called theta. And we saw things with right triangles, and we saw triangles that weren't right. Now, I've been emphasizing all along that these are just two different interpretations of the same thing. There is only one trigonometry. These are the same sine and cosine. And, we've looked at the two different versions of trig because they have different applications. Remember when we did unit circle trig and we had a section on, I guess, harmonic motion? And we looked at the graphs of sine and cosine and how they wave up and down and things like that. So, harmonic motion applications can include things like radio waves, sound waves. We had an example where we pluck a string on a guitar and it causes sound waves. We could talk about water waves, like dropping a stone into a pond and the water creates ripples. So, when you're talking about things in life that have periodic behavior, that perspective on trigonometry can be helpful. Triangle trigonometry also had real life applications, and some of those tend to be things that are more like, what is the size of something, or what is the shape of something? What is the height of a flagpole, right? Or what angle does the sun make with the flagpole? Things like that. And that could be helpful in real life for things like surveying. And then there are also other applications of it. Um, some of which I guess we've seen and some that we haven't seen. Of course, this is pre-calculus, and I'll tell you that in calculus, we continue to use trigonometry, and we see some applications of it there. So now, what are we going to do? What is the third perspective on trigonometry that we're going to do? Well, it's going to be called analytic trig. Analytic trig. What analytic trig does is it says, let's forget about these shapes, circles and triangles. Forget about the shapes. We're going to study trig algebraically. We're going to simplify expressions, solve equations, etc. So this is going to include some of the things that we usually do in algebra, but now with trig functions. Okay, and in fact, we've already seen a little bit of this, probably when we were doing unit circle trig. So I want to remind you something. Recall from an earlier lesson. I think this was actually from the very first lesson that we introduced sine and cosine. Okay, so that would have been near the beginning of our discussion of unit circle trig. We said sine squared of t plus cosine squared of t equals 1 for any number t. Here, you know what? I'll tell you the name of the lesson that we had that in. It was called Trig Functions of Real Numbers. All right, so in the lesson on trig functions on real numbers, we had this. And I'd like to ask you, do you remember why? Do you remember why we said this is true? Why is this equation true for any t value? Well, it came from the unit circle. And we said that the unit circle follows the equation x squared plus y squared equals 1. That's the equation of the circle. Like, everything on the unit circle is a point x comma y that satisfies this equation. And for x, we simply use cosine of t to represent the x value. And for y, we use sine of t to represent the y value of a terminal point. So we derived it in this way back in that lesson, and I think I even said back then that this is an example of a trig identity. So this was kind of our first example of a trig identity. Now, that can also be written in some other ways. Can also be written as, instead of saying sine squared of t plus cosine squared of t equals 1, we could say sine squared of theta plus cosine squared of theta equals 1 for any number. I guess in this case we'd say for any angle. You could say for any number, or you could say for any angle theta. Usually if it's theta, then we're thinking of it as an angle. Because, it's the same thing I wrote above. It's just labeled differently. That's fine. You just label it t or you label it theta. It's just a relabeling. Or there's another way that it is often going to be written in our lessons going forward. We are often going to write this as sine squared x plus cosine squared x equals 1. And I'm going to put a box around this. This is how we're usually going to see it now. This is true for any value of x. I guess at this point I just want to remind you that we use this notation sine squared x to mean that you're doing sine x and then you're squaring it. I'll write it here. Reminder, sine squared x means sine of x squared. It's a weird notation. The way that we put the 2 there, we don't really do that with other functions. We just do that with trig functions. I don't know if I like it, but it's the standard convention, so that's what we're going to do. Now, I've been talking about trig identities, but I don't think I've properly told you what they are, so let's do that. A trigonometric identity. Let's underline it, is an equality involving trig functions that is true for every value of the variables. I'm going to say variables, could be singular or plural. For every value of the variables, provided that both sides are defined. Period. So it's an equation involving trig that's true for every value of x. This is an equation involving trig, and it's true for every value of x. This thing about saying provided both sides are defined, that just means we're watching out for the domain. You know, we don't want to say something that's undefined equals something else that's undefined or anything weird like that. But yeah, we already know the domain of sine and cosine is all real numbers, so you could put any real number in for x, and this does work. They show, trigonometric identities show how trig functions relate to each other. Okay, so the trig identity above that I put a box around is an equation that shows us how sine and cosine are related. This is one of the ways that sine and cosine are related to each other. And that is kind of interesting or useful because if we get enough trig identities and we see, oh, sine and cosine are related in this way, and, you know, sine and cosecant are related in a certain way, we start to see all these connections between the different trig functions, and we see that they are all kind of parts of the same big picture. And in math, we like to see connections. We like to see how different things from math are related to each other. So that's one trig identity. I put a box around it. Have we seen any others? Yeah, we have. More trig identities. We've seen some by this point in the course. We just might not have emphasized, oh, I don't want to say trig functions, more trig identities. We've seen some. We just might not have emphasized that they were identities. Can you think of any that we've seen already? It would have to be an equation involving trig functions. That's true for every value of the variable. Yeah, we've seen things like, how about this one? Tangent of x equals sine x over cosine x. That is another example of a trig identity. We might have written it with t or theta or something else, but we'll just usually use x for the... If there's only going to be one variable, then we usually call it x. Another one that we've seen is secant of x is 1 over cosine of x. You know, that might seem simple. That might seem like that's just the definition of secant, almost. I guess technically when we first defined secant, we called it 1 over x, where x was the point, terminal point value. So, but yeah, this is a trig identity also. Trig identities can be complicated. Trig identities can sometimes be simple. I'm just going to say, etc., that anything like this that we've seen has been a trig identity. It's true for every value of x as long as both sides are defined. You know that there are some values of x where tangent is undefined. That's okay. All we're claiming here is that these two things are equal for any x value as long as both sides are defined. Same thing with this one here. We don't want to divide by 0, but for every x value where both sides are defined, this is true. So at this point, I have a handout for you. So I have posted a list of trig identities in the spot where I usually post worksheets. So I'd like you to take a minute, pause the video if you need to, but go and get that handout. I think it just says trig identities.pdf, something like that. I'm going to show you. It looks something like this. Oh, it's a big list of trig identities. Okay. And we're going to refer to this throughout this lesson and some of the upcoming lessons. Let's just take a quick look through it. All right, let's take a quick look through it. You don't have to know all of these for this lesson. First thing I want to tell you, it looks like there's a lot of stuff here. I'd like you to go grab your own copy, because I'm not going to have it on the screen all the time. But there's a lot of stuff, but this covers multiple lessons, so we're not doing this all today. Okay? Let's zoom in a little bit and look at some of it though. In the upper left, it says fundamental identities. And the fundamental identities include some of the ones we were just talking about. So we've got, there it is, sine squared x plus cosine x squared x equals 1. That's great. Here are the ones that we might call the reciprocal identities. Secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. This one here, tangent is sine over cosine. These are all really good. A couple of other ones that we'll talk about, or maybe we have talked about already, I don't remember. And then we've talked about these briefly when we talked about the unit circle. So those are all under the heading fundamental identities. If I zoom out, you see there's a lot of other stuff here, right? And most of this we haven't seen yet. And some of it seems simple and some of it seems complicated. We're going to get to all of it throughout the lessons. So I guess don't be too intimidated by it. We'll get to it little by little. I do see something else on here that's familiar. Down here, the law of sines and the law of cosines, that has to do with triangles. Now, something I want to point out to you is that I think that I said that in this discussion of trig identities that we were going to be leaving shapes behind. We weren't going to be thinking about circles or triangles. And then all of a sudden there's a triangle on our list of trig identities. So what's going on here? I want to tell you that technically the law of sines and cosines are usually not included on lists of trig identities. Okay? Because I guess if you looked at any of these, like, does this really show how different trig functions relate to each other? You know, take this for example. This shows how sine is related to sine is related to sine. You know, it's not showing how two different trig functions are related or anything like that. And same thing with the law of cosines. You know, cosine is the only trig function to appear. So usually these are not included on lists of trig identities. It was included in this list because I copied this from a book, and I guess I just wanted to say that they're included because they are useful formulas about trig, but technically I think we would say the other ones are really what we consider trig identities. Now, let's get back to writing some notes. Oh, another thing that makes the law of sines and cosines different is that A, B, and C are usually viewed as constants. I should have said that. You know, you do something like sine of A, that's a constant. The triangle has a certain angle, and, you know, it's not really dealing with variables. It's dealing with constants. So sometimes the law of sines and cosines might be referred to as triangle identities. They're kind of a different category. These sorts of things are trig identities. Now, I said something earlier about how we're going to be doing algebraic things, like we're going to simplify expressions, solve equations, etc. So I want to show you how we can use identities to simplify expressions. This is going to be our first type of problem for this lesson. I'll show you the first one, I guess. Okay. Simplify. I'm going to give us two parts. Part A is going to be tan x cosecant x, and part B is going to be tangent squared x cosine squared x plus cotangent squared x sine squared x. All right, I'll do this for us, and then after this, I'll give you one to try. All right, solution. Tangent x times cosecant x. I think a way that we could use trig identities to simplify this is we could certainly use trig identities to rewrite this. Maybe what we could try is rewrite this in terms of sine and cosine. So technically, I just used two trig identities to do that. And doing this is helpful because I see a sine, and I can cross those out and cancel those, and I'll be left with 1 over cosine x. But 1 over cosine x can be written more simply as secant x. Let's put a box around that. So it turns out that this thing we started with, tangent x times cosecant x, simplifies to just this. This looks simpler than what we started with. So that's how we can use these simple trig identities to simplify things. What about this second one? This looks more complicated. Tangent squared x times cosine squared x plus cotangent squared x times sine squared x. What can we do? I think an idea is we could also try a similar strategy of getting it into terms of sine and cosine. So a way that I can do that is I know that tangent is sine x over cosine x. I need this to be squared, though. Cotangent is actually the reciprocal of tangent, so it's cosine x over sine x. So does that help? I used a trig identity to do that. Does it help us? Yeah, that's going to help. That's going to help because when you square a fraction, you need to square the numerator and the denominator. So really what we're looking at is this. There's definitely things that cancel here, right? Let's cross some things out. Cosine squared over cosine squared cancels. Sine squared over cosine squared cancels. I'm left with sine squared x plus cosine squared x. Let's make sure it looks like a squared. It's not sine of 2x. It's sine squared x. All right, so we simplified to this. Hey, look at this. Sine squared x plus cosine squared x. We know that this simplifies to just 1. So that's the answer, 1. And that's a great example of using trig identities to simplify expressions, because the expression that we looked at, that we started with, looked really messy, it looked really complicated, and it turns out it's really just a complicated way of saying 1. For any value of x that you put in here, as long as all of the parts are defined, this will simplify to 1. You can try it. Take an x value, I don't know, pi over 3. Put it in to all of these. It'll simplify to 1, but you don't have to do that as long as you did these steps carefully. Okay, so I said I was going to give you an example to try. So I'd like you to simplify, and I'm going to give you 2 parts also. First one is secant x over tangent x, and the second one is, before you pause the video, I have something to say, so just wait a moment. This is sine theta over cosine theta plus cosine theta over 1 plus sine theta. And my thing that I wanted to say is I'm going to give you a hint for part B. Hint, combine with a common denominator. All right, so now I think you can pause the video and try these two. Okay, ready to go over these. So solutions over here will work on part A. What worked out in the previous problem was getting everything into terms of sine and cosine. So let's try that. I guess we could say secant is the same as 1 over cosine x. I shouldn't say 1 over cosine. I should be clear. It's 1 over cosine x. And then tangent is sine x over cosine x. So what do we do when we have a fraction over a fraction? I think a nice way to deal with fraction over a fraction is instead of dividing by a fraction, we multiply by its reciprocal. Now I see things that cancel. I have a cosine x over cosine x. So this whole thing is 1 over sine x. And what's another name for 1 over sine x? Cosecant x. And that's a good answer for this, that this thing we started with simplifies to cosecant x. All right, this was part A. Let's work on part B over here. So I had suggested that you combine with a common denominator. Yeah, because we have a fraction plus a fraction. If you have a fraction plus a fraction or a fraction minus a fraction, I think that common denominator would be nice to have. But these denominators look so different. What would be a common denominator of these two? Well, I mean, I don't know how much detail we want to go into this, but like, how do you find common denominators? For fractions. Like, what if I asked you, this is a completely different little problem for scratch work as like kind of making an analogy. How do you find common denominators? What if I asked you to find 3/5 plus 1 over 7, and you were trying to combine these? What if you were trying to combine these? You would use a common denominator of, what would you use? 3/5, 1/7. You'd use 35, right? Multiply the two denominators. That's guaranteed to get you a common denominator. So now, looking back at this problem, I think, well, if I want a common denominator, how about I just multiply cosine theta times 1 plus sine theta. That's guaranteed to be a common denominator. For this first step, I'm still going to leave it as two separate fractions, but our goal is going to be to merge it into one. All right, there we go. Multiplied, that's a common denominator, but we have to figure out, what does the numerator get multiplied by? How does the numerator change? Well, instead of just sine theta, this is going to be sine theta times 1 plus sine theta. And instead of this just being cosine, this is going to be cosine theta times cosine theta, which is also known as cosine squared theta. Okay, everybody with me so far? Did we simplify? We're trying to simplify, and it looks like it's getting more complicated, but it's about to get simpler. Because now I'm going to write it as one thing with one denominator. That's what we were really trying to do here. Let's merge these together. That was what I wanted to do. Also, while we're at it, let's go ahead and distribute across the parentheses here, because I think that might help us. So sine of theta plus sine squared of theta plus the cosine squared of theta that was already here. Is it getting any simpler? Or is it getting more complicated? It's one fraction now instead of being two fractions, so that's nice. Hey, guess what? Look at this. I'm going to circle it. We have a sine squared of something plus a cosine squared of that same thing. This equals 1. This part of it equals 1. So this is great. We're applying a trig identity to simplify. So I have sine of theta plus 1 is my numerator. So are we done? Did we simplify? Or can we simplify further? Look at how perfectly this is working out. Look at this. Sine theta plus 1, sine theta plus 1. We can cross these out. What are we left with? Does that cancel out to what? What does it become? It becomes a 1 up top. Something divided by itself is 1. I'm trying to emphasize that because sometimes I see students cross things out and call it 0. No, this crosses out and becomes 1 because it's a number divided by itself. It equals 1. So 1 over cosine, this is also known as secant theta. That's the answer. So this problem was actually just a really complicated way of saying secant theta. And we did the simplifying by using common denominator and a trig identity and canceling. Canceling is sort of an algebra thing, right? Common denominators is kind of an algebra thing. So that's what I mean when I say that we're applying some algebra skills to trig functions. Let's talk about this. Note, we just found in the last problem that we just did, there's a whole bunch of steps, but ultimately what we found was that this expression that we started with, after a bunch of steps, it simplifies to secant theta. That's what we found. That was the whole point of that, right? We could say this is a new trig identity. It's kind of like we just found a new trig identity. Right? If you put a box around it, maybe you want to put a box around it and add it to that handout of trig identities. I'll say the steps we did prove that it is true. The steps that we did justified our answer that this expression is, in fact, equal to secant of theta. It simplifies to secant of theta. So the idea is that this is why there are so many trig identities, and there's a lot of them on that handout, but then you could also make new ones. You just kind of give yourself something and simplify it, and you could call that a trig identity. Now, is this a useful trig identity? Probably not. It was useful for practice, but I mean the trig identities that wind up on that sheet that usually wind up on official lists of trig identities they're usually the ones that turn out that turn out to be useful in some other ways. Okay, but nevertheless, we did kind of find a new trig identity, and the steps that we did prove that it's true. And in this portion of the course, we're going to be interested in proving trig identities. And we're going to be interested in proving the identities that are on that handout and proving ones that are not on the handout. So, if we are given an identity and asked to show it is true, Our goal is to explain, maybe explain's not the best word. Maybe I'll say our goal is to show why the left-hand side equals the right-hand side. So this is going to be a different type of problem besides just simplifying right-hand side. Besides just simplifying expressions, we are going to have some problems that say prove the following trig identity. And you're going to be given both sides, the left-hand side and the right-hand side. And I'm going to tell you some guidelines. Guidelines for writing these little proofs. I'm telling you what the goal is because it's a different kind of problem than you may have seen in math classes, or maybe you've done proofs in like a geometry class at some point, something like that. But basically, you're going to be given a statement that is true, and your job is to explain why. So if you simply just say the statement is true because it says so, you're not going to get any credit for that. The credit is for what steps you show to justify this. So we'll be doing examples, but let me give you some guidelines. I would suggest that you start with one side. There's a left-hand side and a right-hand side. Start with one, usually the more complicated one. If one of them looks more complicated than the other, I would suggest you start with the complicated one and try to, in step 2, use known identities to simplify. Another guideline is, this is the last one, it's just three guidelines for us to follow, is if you get stuck, you don't always have to do this. You don't always have to do step 3 here. But if you get stuck, try converting everything into terms of sine and cosine. Okay, so we can do that with some simple fundamental trig identities, you know, sine x over cosine x, things like that. So I'm going to show you one of these problems. New type of problem. So some of these problems might say, prove the following identity. Another word that they might use instead of prove is they might say verify. Verify the identity. It means the same thing, verify or prove. And we're going to be given for this one, secant x cosecant x equals tangent x plus cotangent x. So our job, and I'm going to walk us through this, our job is to show why is this true for all values of x. You can't just plug in a specific value of x. Don't do that. Don't just put in like x equals pi over 3 and show that the two sides are equal. That doesn't prove anything. That does not prove this trig identity, because the statement that is being said here is that secant x cosecant x equals tangent x plus cotangent x for all values of x such that both sides are defined. So if you prove it for one value of x, that's not good enough. We need to show that it's true for all values of x. Practically, we can't plug in every possible value of x. So that's why we're going to use simplifying, algebra kind of things, canceling, whatever it takes. All right, here's what I'm going to do. I'm going to start with one side. Now, which side looks more complicated? I'm going to say maybe they look about equal, so it's a judgment call which side you want to start with. I'm going to start with the left-hand side. I'm going to say that secant x cosecant x, I want to use known identities to simplify it. And I think I'm going to try 1 over cosine x times 1 over sine x. I just used some identities. Well, one thing that this lets me do is I could write it as 1 over cosine x sine x. But I feel like I'm at a dead end here. Like, I'm trying to show why does this equal the right-hand side? And I don't really see why does this equal the right-hand side. So here's what we do. We get this far, we rewrote the left-hand side as much as we could, and then we move on to the other side. So the guidelines said start with one side. It doesn't mean that that's the only side we're going to deal with. Start with one, and then move on to the other if you need to. So the other side, tangent x plus cotangent x. If I could use identities to rewrite this, my goal is to show that this can eventually, after a couple of steps, something, my goal is to show that this simplifies to the same thing that the left-hand side simplified to. That they both simplify to the same thing, therefore they are equal. Let's get this into terms of sine x and cosine x. So, are these two things equal? I mean, they should be, but why are they equal? So we need to show more steps, because we have not really shown why these are equal. The only reason I'm saying I think these are equal is because it was given in the problem. If it says prove the identity or verify the identity, it's going to be true. It's not going to be a trick question. Okay, so what do you think? Can you think of any ideas for what our next step should be to simplify this? So I've got an idea. Let's do a common denominator. Multiply the two denominators like we did on that other problem. Because it seemed to help with the other problem, so maybe it'll help here. Oh, look at this. This becomes sine x times sine x. This becomes cosine x times cosine x. So this simplifies to... See what's happening here? I think this is going to work. By doing a common denominator and merging this into one fraction, I wind up with 1 over cosine x sine x. These are the same thing, right? We started with the left-hand side and simplified it to this. Then we started with the right-hand side and simplified it to this. They both simplified to the same thing. So I will say we showed left-hand side equals right-hand side. So the identity is true. And all of this is the answer. And you need to write something like this. All of this. Okay, so these are the steps that justify why this trig identity is true. And I just am trying to emphasize that on these problems, you essentially know what the answer should be. The left-hand side should be equal to the right-hand side. So you don't get any credit for just saying that they're equal to each other. You're graded based on correct work shown to justify why these are equal. They're equal because they simplify to the same thing. Sometimes you get lucky and one of them just simplifies, one of the sides just simplifies to the other side. And if that happens, then you don't even have to do both sides. You just start with one and do a bunch of steps until it equals the right-hand side. That happens if we get lucky with a problem. But if it doesn't, then you just deal with both sides until they both become the same thing. There's kind of so I said if a problem says verify the identity or if a problem says prove the identity, then what's given to you will be true. It's not up for it's not a question. It's not asking is this equal to this. It's telling you this is equal, explain why. There's another type of problem I suppose that you could see where maybe a question might say, is the following trig identity true? Yes or no? Explain why. And that would be very clear. If it's stated that way, then you know that it's up for debate. It's up for you to figure out if it's true or not. But for now, we're more interested in just verify the identity problems. Let's do another. Oh, and by the way, this identity we just verified, it's not on the list of identities. It's probably not a super important identity, but these are all good practice for us to do these little proofs. Verify the identity. I'll do this one also because I think something a little bit different happens in this one. So this is going to say 1 plus cosine theta over cosine theta equals tangent squared theta over secant theta minus 1. Let's move the page a bit. I think we're done with that old one. All right, so what do I want to do? Solution, I want to start with one of the sides. Now, the thing said start with left-hand side or right-hand side. I don't really know which one looks more complicated, so they both look complicated. I'm just going to start with the left-hand side, and you can abbreviate it LHS. So 1 plus cosine theta over cosine theta. How can I rewrite this in another way? Does it simplify to something? I see a cosine over cosine, and that might be nice to work with. So how about this? Earlier, we talked about having two fractions and combining them into one. Right now, I have one fraction, and I feel like it might help if I separate it into two. I separated this into two fractions. The reason I did that is because, this whole thing is going to become 1. This whole thing, by the way, is secant theta. So secant theta plus 1. Let's stop here for now on the left-hand side, and let's say I don't think there's any further work that I'm going to do on the left-hand side. I'm trying to show that this equals this right-hand side, which looks pretty different right now. Let's move on to the right-hand side, and we're going to hope that the right-hand side simplifies to this. It should, if we get there. All right, let's start with the right-hand side. Tangent squared theta, and you should write it. You should write the thing that you're starting from. How can we rewrite this in a way that might help us? I mean, you could look at the list of identities that we know. How about the fundamental identities? Is there anything on the list of fundamental identities that might help us? I don't want us to use everything on this sheet today because there's a lot of stuff on this sheet that we have not proved yet. We haven't justified why they're true. But I think in this class, I think we've seen all the fundamental identities already. So let's look at these fundamental identities. Anything that looks helpful. Looking at where we're at in the problem, we've got tangent squared something, secant something. So do we have anything in here that involves tangent squared or secant? I mean, this involves secant. We could try this. This involves tangent squared. We could try this. That's pretty specific. It's not only is it tangent, but it's actually tangent squared. Hold on, let's take a look. So if we could somehow use this identity to rewrite the numerator, it might help us get the numerator to be something involving secant, And then we would have a numerator that is in terms of secant and a denominator that's in terms of secant. I think that might be the way to go. So let's do that. I'm going to do a little scratch work for this step. Scratch work. The identity that caught my eye from the list was this. Now, on the list, it was written with the variable called x, and I'm rewriting it with the variable called theta because it's just a label. As long as you change it on both sides, this is the same identity that's on the list. I think that from this, we could say that tangent squared of theta is equal to secant squared theta minus 1. I'm going to kind of compartmentalize this. That's my scratch work for this step. So tangent squared theta can be rewritten in this way. So my numerator can be secant squared theta minus 1, and my denominator has not changed. So I found a fundamental identity that I thought would help us get this into terms that are useful for this problem. For this problem, I thought it would be useful because then we have a secant up top, a secant on the bottom. And from here, what do you think? Is there some kind of canceling we can do? It's a little tricky because the top is squared and the bottom is not squared. I look at the numerator and I say, wait a second, something squared minus 1. We can factor. I told you we were going to be doing things from algebra. You can factor this into secant theta minus 1, secant theta plus 1. And the denominator is still unchanged. Well, that factoring seems like it was a pretty key step. That's perfect, right? Because look what happens. Cancel secant theta minus 1 over secant theta minus 1. And what are we left with? We're left with just secant theta plus 1. And that's what we were trying to get, because that's what the left-hand side simplified to. So the right-hand side and the left-hand side do both simplify to the same thing. And, you know, in the previous problem, at this point in the problem, I wrote a sentence. I said, we showed the left-hand side equals the right-hand side, so the identity is true. You could write that sentence here. Or you could say something like left-hand side equals right-hand side, check. That's just like a little abbreviated version of the sentence. And I'll say that's good, we're done with the problem. So in these steps, I mean, you know, there might be some flexibility. There might be some flexibility in what simplifying steps you do. So you might find a different way to prove this that uses some other simplifying steps or some other trig identity or something, and that would be okay also. Okay, I've got one last thing I want to say. So I've been talking about, on this list of identities, this list, we mostly today were looking at these fundamental identities. So we know why sine squared x plus cosine squared x equals 1. I'm going to underline y. We know why. We talked about that earlier. We know why tangent x is sine x over cosine x. That was from the definition of tangent back when we were talking about the unit circle and when we first introduced tangent, right? We know those ones. I would say that we know why secant is what it is, why cosecant is what it is. Those were all discussed when they were first introduced. There's a few other ones, maybe 5 other ones here. I'm going to point to them. This one, 1 plus tangent squared equals secant squared. This one, 1 plus cotangent squared equals cosecant squared. And then these three that are also listed under the fundamental identities. So why are the other fundamental identities true? Should we prove them, verify them? Well, my answer to this is we derived them in an earlier lesson, and I'm not going to go through the steps again, but I am going to just tell you when we did this. It was the lesson on trig functions of real numbers. And I'll say it was near the end of the lesson. So we did actually find those trig identities. So I think everything that's listed on that sheet under the heading fundamental identities, we know why all of those are true. What does it look like? There are 10 identities on there, and we know why those 10 identities are true. So I think we are fully justified in using any of those 10. Now, as for the rest of the sheet, that's what some of the upcoming lessons are going to be about. So we'll use them when we get to them. Okay? All right, so we're going to wrap things up here. All right, so when this lesson started, I said it was the beginning of a new chapter. So this section was kind of introducing the concept of trig identities. What can they be used for? Well, one thing they can be used for is simplifying expressions. We did some problems like that. And you know, in math, we like to simplify things, so that could be useful. But they can also be used for some other things that we'll see later. I guess you could also say trig identities can be used to derive other trig identities, which might seem like an endless regression, but there are other uses as well. I guess you could say it's also useful just because it shows us how the trig functions are related, and that's sort of informative to us. You know, how are these functions all related to each other? This is how they're related. Anyway, yeah, we'll see some more concrete uses of them coming up. So the plan is that after this one, the next 2 video lessons are going to be more trig identities, and they're going to address a lot of the other things on this sheet. Okay, so addition and subtraction formulas, double angle formulas, half angle formulas, what is all that stuff? That's kind of what we're going to talk about in the next 2 videos. And then after that, we're going to have 1 or 2 video lessons about solving trig equations. So that's the stuff that's on the horizon. All right, so everybody have a good day. I hope everyone's doing well, and I'll see you soon.